All right, I'm excited to bring you some new work from our research group on a neural network embeddings-based similarity search method for atomistic systems. This work was done by Yelin Yang and Mingji Liu, who recently graduated, and was published in Digital Discovery. You can find it at this URL, and you will see that in the video description if you look. Work was supported under NSF DEMREF Awards CBET 1921946. So thank you for that. All right, in a nutshell, what we have is a problem that it's hard to find atomic structures in databases. So atomic structures are defined by XYZ coordinates, atom types, and unit cells, but these are defined by float numbers and atom types, and they're not invariant to translations, rotations, permutations. That means you can take the coordinates and shift them in XYZ space, and they're the same structure, but they have different coordinates. Or you can rotate them, or just change the order of the atoms, and you get a different set of numbers that represent the same thing. So that makes it very difficult to search because you don't know how the numbers were put in there in the first place. So in this work, we provide a solution to that by using something that I'll show you is an invariant atomic environment vector. And it doesn't matter if you translate or rotate or permute the system, you get the same vector. So that solves one problem. And then we couple it with an approximate nearest neighbor vector search. And that's important because you can't index float numbers very well. And indexing is one of the ways you get high performance in database searches. So what we do instead is use this approximate nearest neighbor vector search. And I'll show you that we can use this to find atoms or molecules or bulks or surfaces that have similar environments or that are similar to the query. And I'll also show you that the results of our search are similar in different ways. They're similar in geometry, which is typically what we desire, composition, energy, and electronic density of states, and by proxy, other properties. All right, so graphically, here's what happens. We have molecules or bulk systems or surfaces over here on the left, and for each one of these atoms, we can create an invariant vector. So that's just going to be a long vector of numbers here that define the local environment around each atom. So this one will have elements that indicate there are hydrogens around it. This one will have hydrogens and oxygens around it, and so forth. And this could be a database of, say, 10 to the 9 molecules, or many bulks and systems. And so we get a set of vectors for all of these atoms. And then we use an approximate nearest neighbor vector search algorithm. We used FAISS. And what happens there is it creates something kind of like this decision tree where it does find some centroids and figures out groups of the vectors that share a similarity. And then if you want to find an atom in there, you make a query vector and you walk down this tree until you find out that the query vector is close to all of these. And then we can do a search in this small space very efficiently, and we don't have to compare all of the things over there. All right, so the overall framework is you first need a database of the structure. So that can be something like QM9, Materials Project, OC20, or any other database of structures. And then we need to create the vectors. So we focused primarily on GemNet. In the paper, we talk about a few others, but GemNet is a graph convolution neural network. And there is a layer in there called an embedding layer that the atomic energy is typically linear in, and we use that vector as the atomic environment descriptor. And what that means is atoms with similar embeddings have similar atomic energies, and that's intuitive for the most part. Then you create the index, so that's where you group all of the vectors. This is all done in advance, and you have an index. Then you can take some subset of atoms here to generate a query vector, and then you can search and figure out which vectors are the closest, and whichever ones are closest are the ones that you're looking for. All right, so that's the overall idea. You prepare a database, generate the embeddings, create an index, and then you can query it efficiently because we have that index. Okay, so Let's talk about a couple of examples. I have three different examples. One is, the first one we'll talk about are molecules, geometric similarity. And so what we did was take benzene as a query molecule and then find all of the molecules in QM9 that were considered close to it. And so B, C, D, E, and F are the top 5 that came out with this specific kind of similarity argument we used. You can see almost all of them have the 6-membered ring. There's a couple here that have nitrogens in them, but all of them have these carbons that have 1 hydrogen in them, and then there's some heteroatom similarities as well. There are lots of ways for you to define similarity. This could be find molecules that have this kind of CH structure in them. You could use, I'll show you later some examples where you can combine logic, where you might want to exclude things that have heteroatoms, for example. But in this case, it gives you some idea of the geometric similarity. We also showed that this similarity implies energetic similarity. And so the way we did that is we used a atomistic potential called flare, and you can train this machine learning model to give you the energy of a configuration by training it on the energy of other configurations. So if we look at the green dot here, the green line, what's happening here is we're just randomly selecting any molecules from QM9 and then training the flare model on it. And you can see the errors are very high. These are, after 15 configurations, we still have an error of over 10 EVs in the energy. That's enormous. So randomly picking structures does not lead to a very good model. And here I have in red the Morgan fingerprint, so those are coming down here. You get a little bit better, but you can see we still have an error of something like 5 EVs. And that means that these configurations are more similar to benzene, that's the energy we're calculating, but they're not very similar. And if we contrast that with the GEMNet search, what we see is that by 10 configurations, only 10 other molecules, we get very, very good 40 milli EV errors in the total energy. So obviously that means that the energies of these molecules nearby are similar to benzene, which is why we get such good results. So this GEMNet embedding, which I mentioned before, these are vectors that the atomic energies are linear in. What you would expect from this is that when you find similar molecules, they have similar embeddings and therefore similar atomic energies. We can combine substructure search with logic. So here we want to find molecules that contain, say, an OH and an NH2. So we generate vectors for this combination and vectors for this combination. And then we find all the ones that match this and all the ones that match this. And then we do a logical AND between those sets to find molecules like this one that contain both an OH and an NH2 in similar environments as this. So we see here we have a CH2, here you have a CH2, here we have a CH2, and here we have a CH2. So lots of interesting ideas that you can use in combining the search structures and the queries. All right, let me talk about bulk queries just a little bit and kind of motivate how we thought about it. So over here we have a structure that we were interested in finding a match for this kind of oxygen. So let's say we picked one of them. You can find oxygens that have an environment similar to this one by creating the vector for this and then searching the QM9 database for similar vectors. And we see B and C are basically the same kind of material, just in different crystal structures. So it shouldn't be surprising that we could find those. But over here we find one that is cobalt zinc, and the embedding vector here is somehow similar to the one here. And so we should think about how is that, why is that possible. So over here we have copper aluminum, down here we have cobalt zinc. We can do this with atomic adsorbates as well. So here again we pick an oxygen adsorbate that is sitting on top of a palladium silver surface as our query atom, and then we find down here is a related adsorbate that's similar, Here we have a palladium thallium, and you can see in all of these cases we have oxygen bonding to palladium with some neighbors. And so over here we have palladium silver, but there are some gold atoms in here. And it's kind of surprising to see this one in here, where you might wonder how is thallium similar to silver in some sense. And we can look at the atomic density of states on the oxygen to see what this similarity means. So what we have here is the query atom. This is what the density of states looks like in the query atom. And in these three examples, we show overlaps of what the density of states on the other systems look like. So here you can see for B, that's this one, we have oxygen that basically only sees this palladium and this silver. It's almost identical in the density of states. For C, there's overlap, and it's a little bit of different, but you see the peaks on the found query results are quite similar in nature. And then over here on D, not surprisingly, it's almost identical. So that tells us these embeddings, in addition to being relevant to atomic energy, they must, when they're similar, they also describe atoms that have similar electronic structures. Now, if we compare that to random oxygen atoms in other systems, you can see that they're not similar at all. So here are 4 different examples of randomly selected oxygen atoms. And so it's not the case that all oxygen atoms look similar, only the ones that we found are actually similar. We can do more complicated adsorbates. Here we look for acetylene that is like this. So here we have acetylene on copper silver, and we would like to find related acetylene configurations, and here are a few that are shown. Not surprising, there's 2 that contain copper, but this one is kind of surprising. There's a germanium, palladium, bismuth alloy that has some similar embedding. And we can again go back to the electronic structure and see that if we compare what the query electronic structure looks like, it's quite similar to these other ones. So especially this unusual germanium palladium alloy system, this is an acetylene that has a similar electronic structure and probably similar energetic properties as the other ones. And so this could be a way to look for similar reactivity or other kinds of properties that we might be interested in. All right, so in summary, this paper is about an invariant vector-based fingerprint that we can use with a nearest neighbor vector search algorithm to find structures in atomistic databases. I showed some examples that it works for molecular, bulk, and surface structure systems, and I showed you the neural network embeddings from this graph convolution method are especially suitable for this task. These embeddings are related to atomic energy, and we've shown that atoms with similar embeddings frequently, at least in the examples we showed, have similar projected density of states. All right, that's the quick summary of our paper. I hope you'll check it out, and I hope you find it interesting and useful in your work. Thanks. If you enjoyed the video, please like it, subscribe to the channel, and let people know about it. Have a good weekend.